Yep. Okay. So my name's Reid Wightman, and I'm a vulnerability researcher in the industrial control systems space. Um, and this is gonna maybe, hopefully, be two talks in one if I have time for the section two. But I want to talk about what is insecure by design and how industrial stuff works just a little bit, and how I've done some weird things with Suricata to deal with some of this insecure by design stuff. So I'm a vulnerability researcher at heart, but I work in the industrial space. And in ICS, if you know anything about it, you know most of the stuff, the protocols that we deal with are unauthenticated. There's no data integrity. There's basically no security in any of the kind of industrial protocols. Um, but so I find a lot of bugs or flaws or whatever people call them in the industrial space in the stuff. And there's two sides to that, right? There's one that are genuine vulnerabilities. So there's things like, oh, there's OS command injection in a web application. Like that, okay, I can write a signature for that. But I want to write detections that look for some of the weirder stuff. So, like the actual industrial protocols work. And there's kind of two aspects to that. One is you want to be able to fingerprint devices so you know what is actually on your network. And then two, you want to detect somebody trying to do bad stuff with those network protocols. And you really, ideally, you want to join the two kinds of detection together. Um, and so, in the industrial space, of course, we have no auth or whatever. There's a lot of protocols out there that just don't have authentication. And if a bad person can learn how to use that protocol, they can cause some change in a process control environment. So again, we want to differentiate what is normal engineering access, what does that look like, versus what is somebody that's trying to do something malicious on your network. So I always like to talk about Modbus. It is probably way over talked about in the industrial space, but it is like the normal, like the, I guess, canary network protocol for the industrial space. It's implemented by almost every product out there. It's used in like every facility I've ever been to in my life. It is insecure by design. It has been used in some malware recently. There was in 2024, there was a Lithuanian made heating controller that was attacked by some adversaries. This heating controller happened to run heat for a couple of buildings in Kyiv in Ukraine. And this was the Frosty Goop malware. So it actually issued some Modbus commands to this controller to shut off heat. And so I like to say, well, how would I detect something like this, right? Um, and so, the way Modbus works, and I'll have a little bit of examples of just packet layout, is it's request response pairs. So the client connects up to the field equipment or the control device, and it issues a request. That request might be a read request. In other words, give me the status of some sensors you see out there in the field, or it might be a write request, which is like either operate some IO directly, or you might be telling it like, hey, there's a control parameter that I want you to change, and your internal program will then take that new parameter into consideration and make adjustments to the outputs based on what I want. Um, this is kind of how Modbus works. This is how a lot of the industrial protocols work. A lot of them are pull response. There's a few of them that do like a publish subscribe model where you can issue a command to subscribe to a certain data point, and then that field equipment will just send you updates periodically. But for the most part, people do this pull response thing. So you want to write some detections for this, right? You want to write a detection for an attack. Well, the normal way is you write a rule using Suricata and you say, well, somebody wrote to some register on a device. I want to, have that as a detection. Well, the question always becomes, is that actually bad, right? There are plenty of devices out there that you write to a heartbeat register just to say, hey, I am a remote HMI and I am connected to you, Mr. Controller. And this is my signal to you that I'm still connected and still active and I haven't crashed. And there are a lot of systems out there that will take that heartbeat message and will treat it as okay, I'm in remote operation mode. That means there's an operator at a workstation that's going to click around and make changes and adjustments to me. And if I don't see that heartbeat for a while, then I'm going to go into local control mode. I'm going to assume there's no operator at the helm. I'm going to, go into my default operating state. And the question then is, all right, so a write command, is it good or is it bad? And that depends on the device. So here is an example of the Modbus map from a generator. This is a generator that's commonly sold in the United States and in Canada. It's a backup generator for big buildings. I won't name names, but it's there. So this is an example of just a very small snippet. There are thousands of control points and settings in this particular generator. I wanted to highlight this section though, because this controls the output frequency of the generator. If you live in Europe, your AC power runs at 50 hertz. If you're in North America, Canada, your AC power runs at 60 hertz. So somebody changing this setting in your generator can be bad. I mean, your laptop power supply will deal fine with power coming at the wrong frequency, but your air conditioning compressor will not function correctly. You can short out the AC compressor and break it, and smoke will come out. It won't be a good day. And so that was the Modbus map for a generator. Now, this is the Modbus map for an inverter. This is a device that takes DC power out of batteries or off of a solar panel and provides you AC power out. This also has the same setting where you have an output frequency, but you can see, on this example, the register for setting the output frequency is register 42324. Over here, it's this other register 40286, and the values that you write to that register are different depending on the device, right? So it's the same setting, but it's two different registers that you're writing to with two completely different value scales that you would expect to see in that register. And so you want to be able to differentiate this, right? So option one is you write a Suricata rule that just says, hey, anytime anybody writes to any register, we're going to log it. And we're going to have some external system that takes those Suricata logs that will have an asset identity map, and then we'll join the three things together. I don't really like this because like I said, it's three tools. So you have the Suricata logs, you have the asset inventory map, and then you have a tool that's joining the two things. That requires three things functioning perfectly correctly in order for you to get like an alert that tells you, hey, somebody is messing with your output frequency. This is really bad. The other method is to try to do everything in one system. And so that's what this talk is really about, is trying to do all of this in Suricata. And the question then becomes, okay, how are we going to do this? So there's the somewhat obvious way, which is like use the Suricata configuration address groups. You can edit the Suricata YAML file. You can go out and figure out the IP addresses of all your different equipment, put them in an address group, and then you can have rules that use these address groups. I don't like this that much because I'm a researcher. I sit in my basement and write Suricata rules. I don't get to go out to the 1,000 field sites where we have sensors installed and find out all the IP addresses of all their equipment. And they, frankly, don't have those address maps either. So I'm going to have to do something to discover them. And what I don't like about this too is like I have to edit this file, and anytime you edit a config file like this, you could make a mistake, something silly, and maybe Suricata isn't even loading after you've modified it. The people that would have to modify this might not be that technical. So this is kind of, to me, a non-starter. So I popped into the Suricata Discord server, right? And I was like, hey, I'm thinking I need some kind of new detection keyword, something where I can have a mutable IP address list. And so Felipe and Shivani both chimed in and they were like, you can do this with datasets. Like, check out the documentation over here. And I never would have found out how to do this if it weren't for them. So thank you for that. So this is an example of using datasets with IP addresses. This first rule that I have up here is an asset identification rule. So this will take a Modbus response. So this would be a Modbus function code 43 response. And if you don't get the bytes, don't worry about it. I can go over it in detail later on. But basically, Modbus function code 43 is a device identity command, or partially. There's an asterisk there, and I'll go into that asterisk in section 2. But it's a Modbus device identity command. A lot of devices support it, but not everything supports it. And it will, if a device is probed with this command, it will usually tell you its manufacturer, make, model, sometimes even the firmware version that it's running, that sort of thing. So I have this rule that looks for this kind of response where the X's are in the content check. There would probably be some manufacturer data or something like that. And If the response matches, I would put it in this data set. I would put the source address of the packet in this data set, which I'm just going to call DS vulnerable generators for now. And I would back that data set up with a file, the gensets.list file. Then I would have a second rule that looks for the write operation. So this would be that Modbus address 42324, and I would look for somebody trying to write to that Modbus address. And if the IP address of that write is in that data set, then I would actually make an alert. So this is actually pretty good, right? But step one of this relied on some network traffic that I'm not as likely to see, because that Modbus function code 43, not every device out there supports it. And most networks, you're never going to see that request if you're completely passive. So if you can put some sort of scanning system on the network and force it to issue that command, you'll see that response. Otherwise, you never will. So I started thinking through, like, how am I going to approach this problem generically and to deal with other protocols? And I also was reading up on some new Modbus standard. There's a thing called SunSpec Modbus. So it's really widely used in the renewable space. And they have their own way of doing identity rather than Modbus function code 43. They store identity information in a particular set of registers. They have this interesting data table format in Modbus where they have to have the manufacturer, make, model in particular registers in a device. So I thought, well, this would be cool to figure out if I can profile these devices passively too. But it gets a little bit annoying because of some limitations in Suricata. The Modbus preprocessor does not let us get at response data. If you look at the Modbus preprocessor docs, you can say, make an alert if somebody issues a read command for a particular register, but you can't say make an alert if somebody read something out of a particular register and it has a particular value. So that kind of leaves us with writing TCP packet rules. And then there's another little challenge to this, which is matching a response to a request is actually a bit difficult because of a little problem in Suricata 2. And it's because I'm a little bit pedantic about protocols. Modbus has some interesting characteristics. Like this is what the response, or actually this is what both the request and the response format of Modbus look like. There's a thing called a transaction identifier. It's a 16-bit integer, and it's how a client knows what response it's getting back to a particular request. So you can do what's called request pipelining, where a client issues a whole bunch of requests all at once. Those responses can actually come out of order. And that can make it a challenge to match up what response is meant for what request. And you have to match those up using the transaction identifier, which means you have to match flow state between two different requests to make sure that you're looking for the right response. And there's another little wrinkle to Modbus too, which is that there's infinite number of ways to request the same data. In this case, this is using that SunSpec Modbus overlay. You can read the device identifier a lot of different ways. So you can say read register 40,000 and read 60 bytes of data or whatever, and you'll get back a payload that contains the SunSpec Modbus header, and then the data table identifier 1, and then the manufacturer of the equipment. Or the client may connect up to the controller and just say, oh, I know it's SunSpec already. I'm just going to go straight to the data, and it might try to read register 40,003, which means that your response is going to have the manufacturer information right away in the packet. So you want to share state between the request rule that matches on the request and the response rule that matches on the response, so that you know where in the response to look for the actual manufacturer data. So my initial thought here was, okay, I can do this with byte extract and byte math. I can extract the transaction identifier from the request rule, and then I can set a flow integer, and then I can match the response rule using that flow integer. And I thought everything was going to work great, but this is an example of Ron not reading the documentation that he mentioned earlier. I read the documentation. So the documentation for this says, and I'm not trying to blame anybody for this, but the documentation says, in the case of byte extract is, what's the exact wording here? It says the variable that you extract the data with byte extract into can be used in any modifier that takes a number. And the flow-int documentation says, well, you have a variable name and a modifier and a number value. So I'm like, oh, well, you should be able to use the number extracted with byte extract and assign it to a flow-int or compare it to a flow-int, and everything's going to be great, right? So I write up some rules, and this gets kind of embarrassing to me. So I write up some rules, and I'm like, all right, well, here's me extracting the transaction ID from the Modbus packet in the first rule. I'm using byte extract to just pull out 2 bytes, treat them as an integer, assign them to this flow-int. And this second rule is meant to like match the response. So this is going in the opposite direction. Source TCP port here is 502. I extract the transaction ID from this response packet, and I check if it's double equals to that flow integer we just extracted. And at first, I think everything is working because my rules were matching when I was testing this out. And I think we've probably all experienced this before, where we've like written SuriCata rules and we think we understand how things work, and then it turns out something doesn't work. The reason this first started, it appeared to work, is because of, I don't want to say it's undocumented, but you really do have to read the source code to see in flow-int if the R value of the assignment or comparison is not a float integer or a packet var. It just defaults to the value of 0. And it turns out my Modbus client was always filling the transaction identifier with the value 0, which meant that like in my initial test, like it was like, oh yeah, I see a request, I see the matching response. I see a request, I see the matching response. I thought everything was great. I probably should have looked at the PCAP and figured out what was going on at that point. So that was a little bit egg on my face. So I was like, all right, what am I going to do? I've encountered actually this problem with byte extract before. You can't use byte extract for D size or B size comparisons either. So that's another place where integer values doesn't really work. And I was like, should I fix the SuriCata documentation? Maybe that's like something easy that I could do. And I was like, well, I could do that, or I could start reading through the code. I haven't written C in quite a long time, but I reverse engineer for a day job. So I'm like, how hard can this be? It turns out really easy. I would say from identifying the problem to writing a little tiny patch was only like a couple of hours of like reading and understanding how SuriCata's detection loader works, like the load function and then the match function, and then looking at how smvar does its variable lookup, and just like writing a little bit of cruddy code. And it's not great, but it's on Redmine as issue 8017 with a diff. I was like, wow, this is kind of cool. I'm opening a ticket and I'm like, hey, I see this problem. Here's a fix. Here's an example rules file and a PCAP. But this lets you assign flow integers from data that's extracted with byte extract and byte math. I think it's going to be really cool. I hope it, I'll have to do all the pull request stuff. I am not a developer. Like, I just hack stuff for a living. But back to the original problem. So we can actually now accurately and correctly match responses to requests. I think that's really cool. It's actually not just a problem with Modbus. There's a lot of protocols that work this way. So I think having this ability to track state that's extracted from a packet so that you can match up another packet is like going to be really cool, because it's almost like preprocessor-y, but entirely in the rule syntax. So the dataset stuff worked out of the box. That was cool. But I wanted to think, the next step of this, which was optimization. Right. I had the example of 2 rules. I had a rule where I added an IP address to the data set, and a second rule that does some content checking and then sees if the device is in that data set. I'm like, data set's probably a little bit of an expensive operation to use in all of these content checking rules. I was like, can I optimize this somehow so that I'm not doing a data set lookup for all of these rules that I'm going to intend to write? And I thought, well, maybe I can do this with a flow bit. So I started playing around with a flow bit optimization method. And this is like to say, hey, have I checked the data set already? If I haven't checked the data set already, let's check the data set. And once I've checked the data set, I want to make sure that I, set the flag saying I've already checked the data set. So I need to have 2 rules for that. Thank you. I think Shivani corrected me at my understanding of flow bit assignments in rules, but this is the way to do that. And then I thought, well, there's another way I could try to do this optimization, and let's see which one wins, which was, why don't we, instead of using a flow bit, why don't we look at TCP flags? So anytime a new TCP connection is open, we'll do the check that way. And it turns out this is tons better performance-wise, and I still don't fully understand why. So I whipped up a 20 megabyte PCAP. This was a single client workstation connecting to 8 different Modbus PLCs, and then issuing 40,000 Modbus requests, only one of which should actually trigger the dataset based alert based on device fingerprinting. So method one was that very first method I talked about where I just had the dataset add fingerprinty rule and then the dataset lookup content match rule. So that used 17,000 CPU ticks. Method two was 4 rules. So it had the fingerprint rule, and then it had the 2 flow bit rules for doing the only do the dataset lookup once thing, and then finally the content check rule that used that flow bit to decide whether the thing was actually an attack. That used a lot more CPU ticks, and I still don't really know why. There might be something weird going on with datasets under the hood where, like, Suricata is evaluating the dataset lookup, even though the flow bit is not set. I'm not 100% sure. That was my suspicion just because I played around with, like, making the dataset artificially large, and it actually took even more CPU ticks. But method three was that TCP SYN flag thing, and that thing was by far the winner. It used about a third of the CPU time as the next best method. So I thought, all right, cool. Method three wins. Now I can write up a little Python code to, like, auto generate these rule chains for me. So, if I have a fingerprintable device, this will generate the rule that assigns the device to a data set and sets up the flow bit names for me so that they're all unique and so that they won't mess with each other. I think we've probably all experienced that kind of fun when you're doing, like, a lot of weird stuff with flow bits. So cool. All right, I've got all that working. So that's basically topic one, right? I think that this is like a technique that I don't see many people talking about, but I think it's kind of interesting, not just for ICS stuff. An example of another industrial product, but not an industrial protocol that I encountered recently was this weird, I won't name names, but it was a weird doohickey that controls power stuff, and it has a web server on it. And it turns out there's a special URI/reset. And when you call, or when you get /reset, the device reboots. And so for 2 to 5 minutes, it's not doing what it's supposed to do while it's rebooting, and you can get this URL unauthenticated. And I was like, well, it would be good to write a rule for this. Of course, I probably there's other stuff out there that has a /reset URI, so I probably don't just want a rule that says, did somebody, get /reset? That's an alert. So we did this just by looking at the server banner and saying, all right, here's the server. It's got a pretty unique string for its server banner. If we see that server banner, we add the device to the data set. And then if it's in the data set and we see the /reset URI, we're going to alert on that and nothing else. So cool. So enough about that. That was a fire hose. On to topic two. So there's another weird researchy thing I did in the industrial space, and this one gets kind of more like out there because I don't really have a great solution for it. But back in 2024, I did this research project internally, and it was looking at servo drives. And so, I'm an industrial control systems person. And one of the things that really fascinates me are, like, these, what they call field bus protocols. So these are things that are not Ethernet based. And in this case, I had this servo controller that operates a robotic arm or that operates conveyor belts or other weird things that require a lot of precision. And this thing is controlled with a CAN bus. And that CAN bus is actually the CAN open protocol. And the way that you network this is you have a PLC, a programmable logic controller, that has a CAN open interface on it that operates the servo drive and looks for, like, feedback from the servo drive. And then if you want to do all sorts of fine tuning of this servo drive, you have an engineering workstation that can then tunnel commands through the PLC down to the servo drive to do, like, tuning of that servo drive for, like, super good precision. And the actual devices I was looking at, if you want to follow along with your own fun eBay purchases, because I buy all my stuff on eBay, it's way cheaper. This was a PLC that runs what's called the Code Assist Logic Runtime. It was a PLC made by a company called Schneider Electric. You've probably heard of them. And the CAN open servo drive, just to make sure everything was going to be compatible, I picked up one of their servo drives. And it was pretty obvious to me right away, like, how the protocol tunneling was working, which was there's a can open packet. Like if you want to do this configuration stuff, there's a can open packet that gets tunneled inside of this proprietary code assist protocol. So you're actually issuing commands directly to the servo drive. And it was really obvious to me like how that was done, because we've made pretty good dissectors for the code assist version 3 protocol. But something really weird happened when I was doing this research, and it was the data object that the engineering workstation accessed for like some of the fine tuning parameters on that servo drive. They used an undocumented can open object. So they actually publish like a can open guide that says, here's how to do all the stuff. But this tuning parameter was not in there. And this tuning parameter, I found an internal document that said it was a Modbus gateway. And so this is where the term turducken protocols comes from, which is this thing was, it was, Modbus RTUs shoved inside of a can open packet, shoved inside of the code assist version 3 protocol, which is its own like monstrosity. They like basically reinvented TCP on top of UDP. It's horrific. But I started reading up some more documentation on this whole product line, and it turns out they also have, this is a public standard, the Modbus standard. There's also this Modbus TCP standard, function code 43, subfunction 13. Function code 43, I mentioned earlier, is the identity command. Well, that's function code 43 subfunction 14. Function code 43 subfunction 13 is can open over Modbus. And it turns out this particular product line, you can also tunnel Modbus inside a CAN bus, or inside a CAN open inside of Modbus TCP. So you have like these layers and layers of protocol on top of each other. And I started thinking like, man, this is awful, because I don't want to tell my protocol dissector team, you need to implement me a stack that consists of code assist v3 plus can open plus Modbus. And you need to implement me a completely separate stack that is, Modbus TCP plus can open plus Modbus. I would love to have something that's like a little bit more composable, where I can piece together which dissectors I need based on content checks that I'm doing. And there was a ticket talked about yesterday that was like, can we do something where we extract arbitrary bytes, not numbers, from a packet? And I was like, oh, that actually very interests me. I think I was the only one to raise my hand. And the reason I raised my hand is because of this problem. I would love to have some kind of a syntax where I can extract arbitrary bytes from a packet and then pass those arbitrary bytes to some kind of like secondary rule set. And I originally thought like maybe I would do something where I output the bytes to a pipe, and I would have like a separate Suricata instance that listens to the pipe and expects these to be raw bytes that it's looking at. I don't know what the great answer is here. I was like, maybe we just make some kind of special preprocessor because I'm special. I don't know. And we, have some way of dissecting packets this way, where we can call these special rules with bytes extracted from an existing rule. And probably somebody's going to ask, could you do this with Lua? And I'm like, yeah, probably, if my detection engineers would let me. But they pretty much, I've written so many bad rules over the years that they don't really trust me. And that's fine. They would rather I just stick to regular Suricata rule syntax. But that was kind of my idea. And I guess like one of the downsides to this method would just be preventing infinite loops, because you don't want to have rules calling other rules explicitly, I guess. You want to make sure that there's some way to prevent that from happening. But yeah. All right, I'm on time. So that's all I got. Thank you for coming to my TED Talk or whatever this is. If you work at Industrial Protocols, I'm always happy to chat with people, because I've been doing this for a long time, and it's a strange, lonely space sometimes. So if you have any questions, I'm happy to take them, or ideas.
Thanks. My question is, you used the flow bits to compare stuff. It's really cool. We do it as well. The question is, like, if it triggers, like, can you extract the value? For example, you want to check if
So it's something that I kind of glossed over, I guess. But yeah, for example, if I do a read command, if I do a Modbus read, I can then extract the value from the response message, and I can actually do some sanity checking on that. So if I read that output frequency, for example, from the generator, and the generator says something other than 60 hertz, I could actually make an alert rule based on that using that technique. Yeah, if that's what you mean.
Yeah.
Yeah.
Okay, if you can take it afterwards from the EVE file, for example, from the EVE log.
Yeah. So yes, you can get at the values are in the eve.json. So like if you issue a read command or a write command, those values do get stored in the eve.json, but you just can't write rules that actually like alert based on those values.
Yeah. Okay. Cool.
Yeah. So, if there's nothing else,
I think there's a question over there.
Hi, question. Have you run into devices, because you already talked about how devices don't really speak standard Modbus a lot of the time. Have you been able to solve the problem for if a device doesn't accurately advertise its name when you request its ID?
That's kind of an area of exploration. So you can do that with like, hand wavy matching, because you can basically say like, if I know this device's map and I know like it's got a frequency, an output frequency in this register, well, I can write a rule that basically says, okay, if I see a value here that's 50 or 60, that's a positive sign, I guess. And the thing that I don't know is like you have to have a bunch of those rules put together of like these registers should have confined values. And yeah, it would be hand wavy, and you could say like, okay, if I see a bunch of these different flow bits set or something like that, if I see enough of these flow bits set, then definitively say this device is device X. It's like the Acme water pump or whatever. But that's probably not something that I would ever deploy in production, because like industrial people are too, they get scared about stuff like that, fuzzy matching. But yeah, it's an interesting thought. Okay. Nothing. Oh.
Oh, really?
Quick question. I noticed some rules to map sort of store the transaction ID and then match on it later. I just checked the code. So the parser actually has bidirectional transactions, so it matches up the request and response.
Yeah.
Is that not usable somehow?
I don't know how to get at it. Is it? Yeah. So I don't know if you can get at the transaction ID from. So I had looked at the Modbus preprocessor at least in 7.0 and didn't see a way to actually get at the transaction identifier from a Modbus rule. And definitely I didn't see any way to get at the response values. And there also wasn't any way to get at like the packet data sticky buffer from within a Modbus preprocessor packet. So I couldn't figure it out. I just like kind of gave up.
So this is maybe also a problem of the rule languages not being expressive enough for Modbus.
Right. And I'm kind of grateful that it's not, because it forced me to kind of do this weird thing and fix flow ints, which I think will actually be useful universally. So, yeah.
Right. But I guess from our point of view, I'm hoping that you would provide like a list of things that the parser ideally would do,
sure,
so that in the future you can use it.
All the fields. I mean, that's always the problem. It's like, well, if I want transaction IDs, then I probably also want unit. It's like I also want this, I also want that. So give me it all. Yeah. I hate making too many requests that I'm not planning to implement myself, I guess. Yeah.
Okay. Thank you.
Yeah. Of course.